Hello folks, this is a video on limiting reagents, and this is really just stoichiometry with a purpose. So you can see a couple examples here. We've got hot dogs, we've got buns. We don't have as many buns as we have hot dogs, so we have our buns being our limiting reactant and our hot dogs being our excess reactant. If we look at molecules here, we can see we have 4 moles of H2 and 3 moles of O2 because we need 2 moles of H2 for every 1 atom. We have excess oxygen and our hydrogen is going to be used up first. And that is our definition of our limiting reactant or limiting reagent. Your limiting reagent is just going to be the thing that runs out first. That's going to determine how much you can make in your reaction. Your excess reagent or reactant is going to be what you have extra of. So once the limiting reactant runs out, the reaction can no longer proceed and there's no more products that can be produced. Here's another example. 5 carbon atoms, 10 oxygen atoms, carbon dioxide, so we can only make 5 molecules of carbon dioxide, and there are excess oxygen atoms, which means that our carbon is our limiting reactant. Pause the video here if you need to get down those definitions. Either example works. Let's talk about those s'mores again. We need 2 graham crackers to every 1 marshmallow to every 4 squares of chocolate in order to produce 1 s'more. So if I gave you 4 graham crackers and 3 marshmallows and only 4 squares of chocolate or 1 piece of chocolate, how many s'mores can I make? Well, because that chocolate is going to run out first, I need 4 squares on every s'more. I can only make 1 s'more. I'm going to have excess of our marshmallow and another pair of graham crackers. So I guess if you didn't like chocolate, you could make another s'more, but it wouldn't follow the ratios and the reactants that we set up as our balanced equation. And that just says everything that I said before. Let's take that into another example of a s'more. If we have 50 crackers and 50 marshmallows with excess or more than enough chocolate in this one, which one will be limiting? Well, what our equation says is for every 2 crackers, right? We need 2 of these. We need 1 of these. So being we have the same amount and we need double the amount of crackers, our crackers are going to be our limiting reactant. And we can figure that out using conversion factors and math. If we just do 50s, that's our crackers, and use our mole ratio. So we need 2 moles of S for every 1 mole of marshmallows. So we would need 25 marshmallows in order to make our reactant. That's going to be the one that runs out first. How many excess do we have? We need 25 marshmallows. This is 50 minus 25, which gives us another 25 because we have the same amount. We're going to see how we do that with chemicals as well, but it's really that easy. So we're looking at mole ratios again. These examples are all going to give you moles, but if we had grams, the first thing we do is convert to moles, and then we can use that mole ratio to compare our substances. Let's take a look at a 1-to-1 ratio problem. Now these are the easiest because these are going to be equal. So once we get our moles, we can compare them. So here's our balanced reaction because everything has a 1. It's always a good idea to check just to make sure that you have a balanced reaction to start with, because if it's not balanced, then your mole ratios aren't right. If your mole ratios aren't right, then your amounts aren't going to be right. We have 25 moles of hydrochloric acid, and we have 20 moles of sodium hydroxide. Because it is a 1-to-1 ratio, the one that has the less number is going to run out first. So that's going to be our moles of sodium hydroxide. The question also asks which one would be in excess. So that's going to be our other one. That's going to be our hydrochloric acid. How many moles of excess? Well, we've got to do 25 minus 20, which gives us 5 moles of hydrochloric acid left over. So that'll be unreacted hydrochloric acid. Hopefully this is making a bit of sense. Let's see a couple more examples. So when it's not one-to-one, there's a little trick that we must do. You're going to see how many moles of one reactant. We're going to use our molar ratio to determine how many moles of the other reactant, or other reactants. If we have more than two, then we need to look at each of them. We're going to compare this amount needed to the amount that you actually have given in the problem. So if it's excess, it's no problem. We don't have to figure out which one's limiting. If they give you two numbers, then you have to figure out which one is going to stop your reaction from happening, which one is the limiting reactant. You can also compare both of your reactants to the product if you already have to figure out your theoretical yield. Let's do a couple more examples. Is not one-to-one. We have 5 moles of hydrogen, right? But our problem says that we need 2 moles for every 1 mole of oxygen. If there's no number, it's going to be a 1. We have 3 moles of oxygen. 3 moles of oxygen. We want to know which is the limiting reactant. We're going to pick one. It doesn't really matter which one we're going to pick because we're comparing them together. So I usually just pick the first one they give us. So that's 5 moles of hydrogen. 5 moles of hydrogen gas. To find out how much oxygen we need, we are going to use our mole ratio. So we need 2 moles of hydrogen for every 1 mole of oxygen. So that means we need 2.5 moles of O2. That's what we need. What we have was given to us. So we have more than we need. So hydrogen is going to be our limiting. H2 is our limiting. This is a pretty easy example. If you have grams of each, you at the very least need to get to the moles so that you can compare them. Or you could turn this 2.5 into grams again. That would make sense, but really we just have to compare what they give us in the problem. We can also compare to the product. We'll see that in our next example. If you did pick oxygen, just for the sake here, 3 moles of O2, we would put our 1 mole of oxygen on the bottom, our 2 moles of H2 on top. We would need 6 moles of H2 to react with all of that 3 moles of O2, and we don't have that. So it is definitely true. That's a way you can check which one is going to be limiting. Which one's going to be limiting? If you need more than you have, you've run out. That's going to be your limiting reactant. If you have more than you need, that's going to be your excess. So we can take an educated guess and say that the other is going to be our limiting reactant. That's really all this is. So it's stoichiometry to compare two amounts. Let's do a couple more problems here. Pause the video. We'll go over these in just a second. We have 12 moles of H2 and 7 moles of O. This is our balanced reaction because we have 2 times 2, 4 hydrogen, 2 oxygen, 2 oxygen. So our reaction is balanced. So now we can compare them. Doesn't matter which one you start with. You can kind of take an educated guess as to which one is going to run out first. We've got 12 moles of H2. When we compare them to our other reactant here in our balanced equation, we put what we have on the bottom. So we have 2 moles of H2 for every 1 mole of O2. That's what it says in our reaction. So we would need 6 moles of O2 needed. We have that, right? We have 7 moles. So we have excess oxygen. For argument's sake, let's say we started with oxygen. So we'll do that up here. 7 moles O2. We need twice as many moles of H2 as we do O2 based on our balanced equation. So we would need 14 moles of hydrogen, which we don't have. We only have 12. If we were to compare these to our reactants, to our products, hydrogen gas would give us the same amount back, so it would give us 12 moles of H2O. Oxygen would give us 14 times 2, just like this one here, so O2 equals 14 moles of H2. So the one that produces less is going to limit, it's going to start first. So everything points to hydrogen being our limiting reactant for this one. Hopefully you got that too. For the second one, if we have 27 moles of hydrogen and 12 moles of oxygen, which is the limiting reactant, and how many moles of excess we have. So we have to take this another step, but our first step is going to be the same. We have to compare our moles to each other. So our 27 moles of H2, if we have to find the excess, it makes sense to compare it to the reactant, not the product. Otherwise, you're going to have to go back and do a little bit more work. Either way, our 12 moles of hydrogen, or 2 moles of hydrogen go on the bottom to our oxygen, 1 mole of oxygen on top. That means we need 13.5 moles of oxygen. So this is what we need. So this is what we have. We don't have enough. So because oxygen is going to be our limiting, O2 is our limiting, we have to figure out how much we can actually produce. So 12 moles of oxygen times 2 moles of H2 over 1 mole of oxygen. So our oxygen cancels out. So we can produce, or we need 24 moles of oxygen. No, 24 moles of hydrogen. 27 minus 24. That's what we have. That's what we need. That gives us 3 moles in excess. Hopefully these are making sense. There's 2 more examples. So if you didn't do them, pause the video here. We'll go over them in just a second. For this one, I've handed you 4 moles of phosphorus trichloride and 10 moles of water. 10 moles of water. We need to determine the limiting reactant, and we want to know moles of excess. So again, it makes sense that we compare them to each other. For this one, we have 4 moles of phosphorus trichloride times 1 mole on the bottom of phosphorus trichloride to 3 moles of water on top. Our moles of phosphorus trichloride cancel out. We find we need 12 moles of H2O to react. We need 12 moles. We only have 10 moles. And the last one, let's change our color again. We have 5 moles. So 5 moles of phosphorus trichloride. We've got 16 moles of water. What is the limiting reactant? What is the limiting reactant? And how many moles can theoretically be produced? So we want to compare each of these to hydrogen chloride because that'll already give us our theoretical yield. That's what the whole next lesson's about. So we'll get there. For right now, just know that we need to compare which one runs out first. So for this one, we're going to do 2 equations. So our 5 moles of phosphorus trichloride, we're going to compare to hydrochloric acid, rather. So we've got nothing in front of our phosphorus trichloride. That means 1 mole of phosphorus trichloride to 3 moles of hydrochloric acid. That gives us 15 moles of hydrochloric acid produced. We do the same thing with our given of water. We've got 16 moles of water times 3 moles of water over 3 moles of hydrochloric acid. That's a 1-to-1 ratio. So I'm going to get the same thing, 16 moles of hydrochloric acid produced. The one that produces more is excess. So our H2O here is in excess. The one that stops our reaction, this is going to be our limiting. How many moles of hydrochloric acid can theoretically be produced? That would be 15 moles of hydrochloric acid. So we're going to do some more practice now. If you have questions, make sure you ask them of me or somebody that's on the same lesson as you. You have 3 choices here. You must do one. You must do one. You can do a second for aspire. So these are your options. This is a FET lab where you can work with another person. This is another from a different textbook actually. The FET lab starts you out with sandwiches, so it's a little bit easier, and then we go into reactions. This goes right into reactions of a gas. And finally, there's a straight up practice worksheet, which gives you a little summary. And then I believe there's 9 questions, some of them with multiple parts. All right, see you soon.